In this video, we're going to take a closer look at line integrals. So we've said that a line integral is a kind of single integral, except we're in a 2D or 3D context. So usually single integrals are for 1D context. They're for functions of one variable, and you integrate over an interval. But now a line integral is when you have a function, say, of two variables. So you're in 2D, but it's still just a single integral because we're only going to integrate over a one-dimensional curve. We're not going to integrate over a two-dimensional, all of 2D or a region of 2D. It's just going to be a 1D curve. So that's a line integral. So here's the basic idea. To actually get going with this, we are going to turn this into sort of a more traditional one-dimensional Calc 1 integral. We have the curve. Now, of course, we have to, the details of this curve have to be factored into what we're doing. We learned in multivariable calculus that you can represent or write a curve in a parametric way. So we usually wrote this as r of t, and it would have a horizontal component and a vertical component. This we might write x of t, and this would be y of t. So we have this representation of this curve. Okay. So the first thing to do in rewriting our line integral is to replace x and y in our function with x of t and y of t. From our curve. So you'll see it in an example, but you literally sub in wherever in this formula you have an x, you sub in the formula for x of t, and wherever you see y, you sub in the y of t. So now this is a formula that only involves t. Second step is there's more to this than the parameterized formula r of t. You also have to say where t begins and ends. A and b. If you don't do that, then this could, in theory, go on forever, which you can do, but it's an improper integral. So usually, typically, and certainly at the start here, we have endpoints, a and b. So here's where t equals a, and here's where t equals b, for example. Maybe, or it could go the other way as well. So t is between a and b, and now once we've switched what we're integrating to involve t, we can put in traditional endpoints a and b. Okay. Now the last part is the ds. How do we write ds? Since we're converting everything to t, right? We have t in our variable, we have t endpoints. We want a dt here, but we can't just literally turn ds into dt. There's going to be some extra stuff that comes along with it. Let me show you how this works. And this gets into our usual idea that's at the heart of all integrals, which is we're breaking up what we're integrating over into a bunch of little pieces. And let's take this one right here as the sample. And let me just blow that up. So here it is. And remember, we are integrating ds, meaning that was the arc length. That's literally how long that little part of the curve is. Okay, well, I'm going to make a little right triangle out of it, as we often do with diagonal things. And the ds is made up of a horizontal dx and a vertical dy. And of course, from the Pythagorean theorem, we have that ds squared equals dx squared plus dy squared. Now to get dt involved, I'm just going to divide by dt. In fact, I'm going to divide by dt squared throughout. Okay? And then I'm going to take the square root. And let me just put parentheses around, instead of having dx squared over dt squared, let me put dx dt squared and dy dt squared. Okay. And then if I bring this dt over to the other side, I have an expression for ds involving dt. So as I said before, ds and dt aren't the same. I can't just turn ds into dt. But now I see that I can replace ds with a dt if I also include this square root factor. And so there we go. You may remember this square root. This square root came up in multivariable calculus when we were learning how to compute arc lengths. And it's no surprise, since the ds is arc length here, that would be something that would come up again. Okay. So let's look at what we have. It looks very, very scary, and it is a big mess. But this is a function. This is our original function just written in terms of t. This could potentially be nasty, but in the end it's just a formula involving t. X of t and y of t, what we're going to need to do there is take the derivative of this with respect to t, put it there, take the derivative of y of t with respect to t, put it there, square them, add them, square root, and it's just going to be an expression with t. So now everything here is just some formula, some expression involving t, and we're integrating it dt from a to b. So this is now just a Calc 1 integral. So we've turned our line integral that was sort of taking place in a 2D context into a regular Calc 1 integral. Let's see one example in practice. Your textbook will have lots more examples. Let's look at this example. Suppose we're going to integrate x squared over the curve C with respect to arc length, where C is the straight line from 0, 0 to 3, 9. So let's look at the picture of this curve. It's just a little line segment. It goes from 0, 0 up to 3, 9. Now what we need first is a parametric representation of this curve. And it's not too bad because it's straight. Of course, this is just the line y equals 3x. Now that's not parametric. That doesn't involve t yet. But what we could do is we could just make x be t, and then y, if we just sub that in, right, if x is t, then y is just 3t. So it's like x just is always equal to t, and y is going to be 3 times t, and that will trace out this line. We want t to start at 0 and end at 3, and that'll start us here and end us at here. So there's our parametric representation. I've written x of t and y of t on separate lines, but of course I could write it as a vector. I don't have to, though. I just don't want you to think I did something different from what I did on the previous page. So just could write it like that. All right. So I take this integral, this line integral. So what I do is I replace my function with the parametric versions. Now this function happens only to have x, it doesn't have y, so I just substitute x of t equal t, so that's just t squared. My t goes from 0 to 3, and then in place of my ds I have to put a square root dt, and under the square root I need the derivative of x with respect to t squared, so that's 1 squared, plus the derivative of y with respect to t, 3 squared. And again, because this was a straight line, these two functions were just linear, so the derivatives were just numbers. So this whole square root is just a number. It's just going to be a constant multiple. So that's going to make my life easier when I actually try to do the integral. So it looks like I have a square root of 10 t squared dt. And now this is just a Calc 1 integral, so I would go square root of 10 over 3 t cubed from 0 to 3. I plug in 3, I plug in 0, and subtract. So 27 divided by 3, so 9 square root of 10 minus 0. So 9 square root of 10 is the answer. Again, what did I actually figure out? X squared is equal to a number at every point in the plane. I am just looking at this little slice of it, this little line segment part of it, and thinking what does x squared equal all along there, and I'm adding it up, but weighted by arc length, and that's the result. Okay, so it can get harder if it's not a straight line, if this function is more complicated, and you could, as always in any integral, trying to do it the antiderivative way using the fundamental theorem of calculus. Of course, we all know that that can get arbitrarily difficult or even impossible here, and you may have to resort to a numerical method like Euler's method or something fancier to actually do the integral. But this one was not bad, and so that's how it's done.